Good day to everyone. Today we are going to discuss part 2 of Module 4 for the subject CE 3151. So in this lecture, we'll be discussing the Gaussian elimination. The first method under row reduction is what we call the Gaussian elimination. So this helps now put a matrix in a row echelon form, or better known as an REF. So given a system of equations, we now form these equations into a augmented matrix, meaning we turn them into matrix using the coefficients of each variables and constant. And once we have converted our equations from the system into an augmented matrix, we now follow it by turning it into a row echelon form following this format, wherein the main diagonals now are equivalent to 1 and the lower elements are all equal to 0. So if you could remember from our introduction from Module 2, this is now an example of an upper triangular matrix. So the steps now followed in Gaussian elimination would be, first is that we have to set our upper leftmost element, or your A11, equal to 1, and then followed that the remainder of the first column should be equal to 0. Next step is to set now our A22 second diagonal element equal to 1, and the remainder of your column 2 will now be set to 0. And lastly, we set the last element of your matrix or diagonal of the matrix equal to 1. So if we will have other rows in our matrix, then it would follow that all of the diagonals should be equal to 1, and those variables or those elements below your diagonal should be equal to 0. So to understand Gaussian elimination, let us have an example. So given the following linear equations, find the possible solution for each equations. So first, we convert our three equations to its augmented form. So we'll have 1, 2, 3, 4 for our second equation. That will now be 5, 6, 7, 8. For our third equation, that will now be 2, 3, 1, 2. So after augmenting our equations, we swap our or interchange two rows, wherein we'll have A11 equivalent to 1. And since A11 here is already equal to 1, we can now interchange row 2 and row 3 instead. Okay? But if A11 is not equal to 1, then we'll have to find another row that would be the simplest value to convert to 1. So in that case, our new matrix now will be 1, 2, 3, 4, and then rows 2 and 3 are interchanged. So next step, so first step is to set A11 equal to 1. Next step is to change now the values of the remaining elements in column 1 equal to 0. So with that, we'll now compute for the second row first as negative 2 times R1 plus R2. So negative 2 times R1 plus R2 will give us 0. For this column, we'll have negative 2 times R1 plus R2 will give us negative 1. So negative 2 times 3 plus 1 is equal to negative 5. And negative 2 times 4 plus 2 will give us negative 6. So next, we make this equal to 0 by computing as negative 5 times R1 plus the value of the elements in R3. So we'll now arrive at negative 5 plus 5 is 0. Negative 5 times 2 plus 6 is equal to negative 4. Negative 5 times 3 plus 7 will get negative 8. And negative 5 times 4 plus 8 will arrive at negative 12. So next is to make our second diagonal element equal to 1. So we'll just simply multiply this by negative value. So we'll now have 0 times negative 1 is 0. Negative 1 times negative 1. Negative 5 times negative is 5. Negative 6 times negative will be 6. So next, we want to change the element below our second diagonal equal to 0. So we do that by 4 times R2 plus R3. So we'll have now 4 times 2 plus R3 is equal to 0. 4 times 1 plus negative 4 is 0. 4 times 5 plus negative 8, we have 12. And 4 times 6 plus negative 12 is 12. And then, lastly, we now change the third element on our diagonal equal to 1. And we can do that simply by multiplying now the third row by 1 over 12. Or that is now equal to 1 over 12 times 0 is 0. 1 over 12 times 0 is 0. 1 over 12 is 1. And the last element is also equal to 1. So we now have your upper triangular matrix. So from here, we can now write this equation as, or the matrix into an equation form as 1x plus 2y plus 3z equal to 4. For the second column, that will now be 0x plus y plus 5z equal to 6. And lastly, we'll have 0x, 0y, z equal to 1. And then, since we know already z is equal to 1, then substituting, we'll now have y is equal to 5 times 1 equal to 6, or y now is equal to 1 as well. Substituting z and y in the first equation will now arrive at x plus 2 times 1 plus 3 times 1 equal to 4, or x now is equal to negative 1. So from our Gaussian elimination, we were now able to compute for the different values of x, y, and z. So another example, given the three equations for our system, we now convert this to its augmented matrix form. So for the first column or the first row, we'll have the first equation, second row, second equation, third row is the third equation. So for your first column, that will be the coefficients for the first variable, second variable, third variable, and our constant. So in your augmented matrix form, make sure that all the coefficients for the same variable or unknown should be on the same column. If you will be interchanging the coefficients for each variables, then there will be an error in our computations. Okay, so next, aside from swapping our rows, we could also just simply add or subtract or multiply scalar values in our elements. Okay, so for this solution, since we have already set A11 equal to 1, so we now move on to setting our remaining elements of column 1 into 0. So instead of swapping, we'll just simply follow R1 plus R2 so that this element becomes 0. So we'll now have 1 plus negative 1 is 0, negative 2 plus 3 is 1, 3 plus 0 is 3, 9 plus negative 4 is 5. So next step, set this element equal to 0, and we can do that by multiplying 2, negative 2 to the first row and adding up the value of the second or of the third row. So we'll now have negative 2 times 1 plus 2 is 0, negative 2 times 2 plus negative 5 is negative 1, negative 2 times 3 plus 5 is 1, negative 9 times 2 plus 17 is equal to negative 1. So next step is to make our second diagonal element equal to 1. But since it's already equal to 1, we now move to setting our variable or element below the diagonal equal to 0. So with that, we could apply now R2 plus R3, and we will now arrive at 0 plus 0, 1 plus negative 1, 3 plus 1, and 5 plus negative 1, 4. And the next step is to simplify now our diagonal equal to 1. So we can do that by simply multiplying the third row by 1/4. So we'll now arrive at 0 times 1/4, 0 times 1/4, 4 times 1/4, 4 times 1/4. So we now have achieved your upper triangular matrix. So we could now write our equation as x negative 2y plus 3z equal to 9. Then we have y plus 3z equal to 5 and z equal to 1. So substituting z in the equation of y, will now get a value of y equal to 2. And substituting z and y, the equation for x, will now have x is equal to 10. So we have already solved our values for each of the unknown variables x, y, and z through our Gaussian elimination. So that's it for the first method of row reduction for system of linear algebraic equations. For your references, you can check the following links Thank you for listening. For the next lecture, we'll be discussing Gauss-Jordan elimination.